We have Dr. Mirail Elaj and Professor Alejandro Roman. Mirail is the founder and CEO of Astra-Terra and is a visiting associate professor at Imperial College London. And Professor Alejandro is a visiting senior space advisor at Astra-Terra and chair of the Administrative Committee on Connecting Emerging Space Ecosystems, IAF Access. So I'm going to hand over first to Alejandro for the presentation and partway through. So over to you, Alejandro and Mirail.
Thank you very much, Claire. Good afternoon, everyone. Thank you so much to being here. I'd also like to sincerely thank Dr. Washington Ocheng, Claire Stead, and the Royal Institute of Navigation for the kind invitation, and of course, Astra-Terra. It's a truly honor and pleasure to be here with you today. My name is Alejandro Roman. I'm delighted to guide you with Dr. Mirail Elaj through this exploration of the dynamic relationship between Earth observation, positioning, navigation, and timing, with a particular focus on the transformative potential on low Earth orbit technologies. We'll journey through foundational concepts, examine current innovation, and uncover the powerful synergies that are shaping the future of integrated EO and PNT systems. Today's sessions is structured in two main parts, as you can see. First, we will establish a common understanding in Earth observation and PNT, what these technologies are, how they work, how they interact with space platforms, and low Earth orbit and medium Earth orbit environment. Then we will explore emerging synergies between these fields, including cutting-edge techniques like GNSS reflectometry and GNSS radio occultation. We will through case studies and explore how integrating these technologies can enhance resilience, data accuracy, and global situation awareness. Next, please. First of all, allow me to talk about the space economy. We are living in a huge growing on the space economy. This is a very important opportunity for every country, not only for the developed country, but also for the emerging countries. This infographic from Nova Space shows the space economy, which value in $596 billion and is segmented on the 224 billion space market, 208 enabled solutions that include GNSS and EO integrations, and also 64 billion in uncontracted costs. As you can see, notably, the PNT enabled value exceeds $308 billion, including 219 billion in services and 89 billions in device revenues. And EO accounts about around $21 billion. This is rapidly growing. The services covers climate, agriculture, and security demand. It is estimated that the entire space economy will grow around $3 trillion in 2030. As I mentioned, this is a huge opportunity for everyone. Next, please. Talking about remote sensing and Earth observation, we can define Earth observation as the collection of information about Earth's physical, chemical, and biological system via remote platforms. Next, please. And also, a remote sensing is a subset of EO. It refers to techniques for collecting data without direct contact, usually by detecting electromagnetic radiation reflected or emitted from Earth's surface. Sensors operate in various spectral bands, from visible to infrared and from microwave to radar. Key EO applications include climate monitoring, agriculture, disaster response, biodiversity analysis, infrastructure management. Remote sensing enable mapping, atmospheric studies, oceanographic, and mineral explorations. Next slide, please. We had multiple platforms for remote sensing. We have the satellite-based, airborne systems, and ground-based sensors. All of them has pros and cons. As you can see, satellites offer broad coverage and long-term data continuity. However, they have limitations in spatial resolution and timing flexibility. Airborne systems such as drones and aircraft provides high-resolution data and rapid deployment, but they are restricted in a range and weather. And also ground-based sensors enable real-time monitoring with high temporal resolution, but are limited in geographic scope. Each system serves specific needs, and platform integration enhance situational awareness and decision making. Next, please. We can see here some remote sensing techniques that goes from muography, reflectometry, refractometry, multispectral, panchromatic, hyperspectral, SAR, synthetic aperture radar, INSAR, that is interferometric measurements, LiDAR, gravimetry, photogrammetry, and ultrasound. Each of them has its specific application and specific techniques. Next, please. Speaking about processing and data fusion, next, please. And for example, on image classification, let me go through the process. Next, please. For example, we talk about that we have different platforms for to gather data from many sources like satellites, drones, and aerial photography. Next. But this data needs to have a kind of pre-processing because we need to correct the atmospheric, we need to do atmospheric correction, geometric correction, and radiometric calibration. Atmospheric correction removes distortions caused by the atmosphere. For example, water vapor, aerosols, that affects the spectral values recorded by the sensor. This is essential for retrieving true surface reflectance values. And talking about geometric corrections, aligns the imagery to real-world coordinates using ground points, ground control points, often derived from GNSS, and corrects from sensor motion, terrain distortion, and Earth curvature. And also we have radiometric calibration that converts raw digital numbers into a physical units like radians or reflectance, and compensates for sensor-specific noise, some gain differences, or illumination conditions. Next, please. And after we have this pre-processing, we can extract value from this data. For example, we can have spectral band analysis that involves evaluating specific bands or combination to detect land cover types, minerals, moisture, and thermal anomalies. And also, we have a supervised classification. We have NDVI. We have the texture and shape. All these combination, and there are many others, help us to extract valuable information from this data. Next, please. Talking about classification algorithm, we can have the supervised classification. For example, we have the SVM, the support vector machines, that separates class by maximizing the margin between them using a hyperplane. Excellent for high dimensional data set with limited training samples. And also we have random forest as an ensemble learning method using multiple decision trees, robust to noise, and effective with mixed data types. And also we have a convolutional neural networks that involves deep learning models that detect spatial and hierarchical features, especially effective for high resolution EO data. And also we have unsupervised classification. We can mention k-means clustering and ISO-data. ISO-data is an iterative self-organizing data analysis and techniques algorithm. It is an advanced form of k-means that adapts the number of clusters based on convergence criteria. This algorithm translates raw EO data into actionable geospatial intelligence, such as land cover maps, vegetation zones, or urban boundaries for application in agriculture, disaster management, and environmental monitoring, as we mentioned before. Next, please. This is what we have mentioned, that after all these processes, we extract valuable information from this raw data. Next, please. And the applications is, just for mention some of them, is very broad. Next, please. Well, talking about now signals and image preprocessing. Those are some of the techniques. For example, we can mention data fusion, integrating multiple sensors outputs, is hyperspectral processing that can deal with hundreds of bands for material classification, anomaly detection, identify deviation from normal patterns, change detection, for example, to compare data set over time. This is useful in disaster and land use monitoring, and compressive sensing that reconstruct high fidelity, high accuracy images from fewer measurements, and GNSSR and RO signal processing that we will cover a little bit more in detail later on in this presentation. These processes convert raw data into high quality decision support, as we mentioned. Next, please. Then what are the various applications from remote sensing and Earth observation? Next, please. Earth observation provides critical data for atmospheric and environmental monitoring. For example, we can mention temperature and precipitation monitoring, wind speed estimation, greenhouse gas and pollution detection, oceanographic assessment like biodiversity mapping, urban planning and infrastructure monitoring, disaster detection and emergency response. The diversity of this application shows how EO is central to climate science, agriculture, civil planning, and other areas. Next, please. Also, we have a subsurface observation. For example, we can mention that the geological hazard assessment, like detecting and monitoring fault lines, landslides, volcanoes, mining and natural resource exploration, submarine object detection, and of course, archaeology. The GNSS-based PNT systems enhance this application by accurately geolocating anomalies or objects detected through various techniques. Next, please. Then what criteria is necessary for choosing the remote sensing systems? The answer is it depends. When selecting EO platform, decision makers needs to weigh, for example, coverage, spatial and extent, resolution, spatial, temporal, and radiometric, flexibility in timing, sensor payload, accessibility to remote or hazardous areas, for example, data latency, speeds of availability, of course, maintenance, and a very important aspect is the cost. No single system is universally optimal. The best choice depends on applications needed. Often, hybrid systems provide the ideal balance. Next, please. Let me talk a little bit about the space observation. We covered Earth observation, and now we will cover the space observation that targets celestial bodies, cosmic events, and human-made orbital objects. Next, please. Talking about space observation, as I mentioned, we can use a combination of ground telescopes, radar systems, and space-based instruments like James Webb or Hubble that they help us to monitor the space. Next. And the applications. For example, we can talk about the particle physics, the research support by space-based detectors, deep space exploration, planetary science, space mining, space situational awareness that is critical for detecting and tracking space debris, satellites and near-Earth objects, planetary defense, missions searching for extraterrestrial life, and understanding the origin of the universe. Space traffic management is vital to coordinating satellite orbits and avoiding collisions. Next, please. Another applications is support on human spaceflight, like logistics, monitoring, and infrastructure for mission, settlement, and tourism. Space weather forecasting, predicting solar flares, radiation storms, and geomagnetic disturbances that can impact GNSS and EO systems. Planetary mapping, detailed surface map, or not only on Earth, but also celestial bodies, and mission planning and planetary defense, and sustainability, tracking space debris, and implementing active removal or mitigation strategies. This interconnected view supports the notion that observation systems, whether EO or space-based, must work together within a shared space infrastructure. Next slide, please. And we can mention now about space observation, specifically space weather. This graphic illustrates how the space weather phenomena interact with Earth and space assets. For example, including solar winds, flares, and cosmic radiation, they can impact not only Earth, but also the assets that we have in space. One of the consequences can be the GNSS signal degradation, and also satellite drag. Communication blackouts can occur due to a high energy particle from the sun. Monitoring space weather is essential for ensuring safety of space missions, protecting satellite integrity, and maintaining timing accuracy and signal reliability in PNT systems. Many agencies like ESA, NOAA, and NASA maintains dedicated missions to observe space weather and issue alerts. Next, please. Another concern is the space debris that is a reality now. As soon as the humanity is growing in space assets, also is growing in space debris. We have over 39,000 tracked objects. We have 1.1 million pieces between 1 centimeter and 10 centimeter. And it's estimated that we have 130 million pieces below 1 centimeters. Each one of them represents a high risk because those pieces are traveling around 27,000 kilometers per hour, and it can damage seriously any space assets. And next, please. And also, one of the key points that is very important is not to achieve the Kessler syndrome. What is the Kessler syndrome? It's a potential cascade of collisions. It's a domino effect, increasing debris in density exponentially. Maybe you remember the movie Gravity. In the first minutes, you can see clearly this phenomenon where it's a cascade of collisions that creates more and more debris, and that is a domino effect that make the space almost unavailable for future missions. And maintaining space sustainability involves many activities. For example, the design for DMIS, for example, ESA's Clean Space Initiative, active debris removal, for example, clear space. And also we have international regulations like UN Long-Term Sustainability or LTS guidelines. Next, please. Well, I would like to give the floor to my dear colleague Mireille Eljash to continue this presentation in the next part. Mireille?
Thank you so much, Alejandro, for this. And thank you, Claire, also for hosting us for this amazing webinar. Thank you so much. It's my pleasure to be here. So I'm going to take over to talk about PNT and its future architecture, but my emphasis will be on space PNT, so basically GNSS PNT. So if we start by defining positioning, navigation, and timing to understand better what is PNT. So positioning is the geometric representation in a spatial reference. It could be the WGS 84, for example, and a coordinate system. Again, it could be Cartesian, so X, Y, Z, or ellipsoidal that gives us latitude, longitude, and height. And we need time relative to UTC. However, people sometimes confuse position with location. Location is the physical representation of that position on a map. Navigation, we all use satellite navigation, of course. So this is route planning and execution of that plan. So this is taking us from point A to B, origin and destination, or between certain nodes. It requires positioning information and time together with the derivatives, such as a speed or orientation, and a map, of course. Timing is the determination of the precise user time through calculating the difference between GNSS system, which is an ensemble of very sophisticated clocks that give us what we call the GNSS system on reference stations, and the user receiver, which is the receiver that is present or in our phones, for example, or in our cars or airplanes, and the satellite time, which is the time on the SVs in space themselves. And these are atomic clocks, time given by atomic clocks, which are quite expensive and sophisticated as well. So why does PNT matter to us? PNT is a set of technologies, as we said, mainly through GNSS. Of course, we have terrestrial and other ones that support crucial services that the modern society depends on heavily, including the 14 critical national infrastructure that we have in the UK. We all know that in the US we have much more, but in the UK we have 14, and they range from transportation to telecommunication, defense and security, finance, emergency services, food, space, nuclear, etc. The latest one added was the data centers, of course. Just to give you a little bit of perspective on this, the cost of disruption for GNSS, if we lose it, it could really pose a substantial economic risk. It is valued at 1.7 billion per day and at 7.6 for 7 days. However, I think these are a little bit underestimated, in my opinion. Now, PNT services directly underpin 254 billion of the UK economy. So this is just to put things in perspective about how important PNT is. So how many constellations we have around the world? The legacy ones so far are 4. The first one was the Russian GLONASS, followed by GPS from America and Galileo in Europe. And the latest one is Beidou, the Chinese Beidou. They all, as we can see, use the the L-band frequency, but they have different signals and different modulations as well. Now, how do we measure the performance? ICAO came up with 4 parameters called the required navigation performance. The first one is accuracy. So what is accuracy? Is the conformance of the estimated position solution to the true position. So this is the difference between what the system estimates and where is my true position. And it's usually accepted at the 95% to sigma. And that's the minimum, of course. The second one is integrity. And integrity is actually the ability to inform the users in the event of a failure in sufficient time. That's why we have something called the alert limit. So if we pass that unsafe position, the system is supposed to give us an alert limit where we're supposed to act in good time. This is the time to alert. The third one is called continuity, and this is an interpretation of the system having continuous operation with very minimal or no interruption. The fourth one is availability. So if we have a system that has accuracy, integrity, continuity, we can say that we have an available system, without forgetting, of course, the importance of standardization. So we're getting more and more into a unified standardization where people understand the importance of those 4 required navigation performance. Now, how does it work? How does standalone GNSS work? As we can see here, we have the GNSS ground system or ground segment, which we call the control segment. We have the space segment where the satellites are. We have the user segment. So what is happening on the ground segment? We have reference stations that track the satellites and send those data to a master control station, which is basically the brain of the whole system. This is where the nav message is transmitted to an uplink station. We call it NLES for uplinking to the various satellites in space. In the space segment, the GNSS satellites continuously broadcast signals with timing and location data. Now, these signals, as we know, they travel down to Earth at the speed of light. The user device, which is, like we said, could be on our phone, our cars, etc. The receiver receives those signals from the multiple satellite and tries to compute its time and location. So how does it work? The GNSS measurements, let's talk about them. The first one is the pseudo range or the code phase. As we know, we have a satellite transmitting a signal and we have a receiver receiving a signal. So what we're trying to study here is the difference between the two times, denoted by TR minus TT in this formula. Now, we all know that from, maybe school, that a distance is equal to speed times time. So since we have those two times, we said that we believe that the signal is traveling with the speed of light or at the speed of light. We can apply it to C. Then we can study that pseudo range. Now, in reality, where do we derive this TR minus TT from? Basically, when the receiver receives the code, it demodulates it and it tries to create a replica. This replica creates a time shift, which is the difference or the delay between reception and transmission. And this is translated in TR minus TT that we see in the formula. But then now we have computed one PR, one pseudo range. So to be able to calculate the coordinates of the receiver, we need, we need 4 equations. Why we need 4 equations? Because we have 4 unknowns, and this is the x, y, z, and t of the receiver. So to be able to solve this, like we said, we need 4 equations. That means we need 4 measurements coming from 4 satellites. Something else that we need to have here is a good dilution of precision or a good geometry. The reason why, if these satellites were in bad geometry, that means they're sitting almost on top of each other or close to each other, I will have a phenomena called singularity, which means my receiver could see them as one measurement. Okay. So here we can see that all these equations, they're not linear. So what we need to do to be able to solve them is to linearize them. So we said that this signal is traveling through space. And that's why we call that range a pseudo range. So what kind of errors are accumulated when the signal is traveling through space? In the pseudo range, we know that we have up there the SV orbit. We have the SV clock, so that means satellite vehicle orbit estimation. Even though we try to estimate it, the estimations are not always very accurate, so we're accumulating errors there. We have clock drifts and acceleration, so the clock also has its own errors. When it passes down through the ionosphere, which is between 60 and 1,000 kilometers, it gets ionized. And this ionization causes delays and advances, depends on if we're using the carrier or the signal itself, the code. So these are another type of errors that get introduced to the signal. Finally, in the troposphere, we know that we have humidity, we have temperature, and we have pressure, and all these affect the signal. Finally, when the signal reaches the ground, it faces also a phenomena called multipath, which is the reflected signal that hits an object or a surface. So it's no more a direct signal that is coming to the receiver. So that also introduces a lot of errors in the measurement. So just to give you an idea about the accuracy that we can achieve using a pseudo range and positioning performance, the accuracy is less than 9 meters horizontally and less than 15 meters vertically. So thinking about this, if we were, for example, flying an aircraft, is that a good accuracy? Obviously, the answer is no. We need more accuracy. So what's the answer to this? The first answer is the differential corrections. And how does that work? When we apply differential corrections, we start by a reference station that we know very well its coordinates. Also, we'll be looking at a satellite that we've been tracking, so we know also the coordinates of that satellite accurately. So now we have 2 points where we know their coordinates and we can calculate the distance between them. Now this range is almost error-free because we know the 2 coordinates very well. So we call that the geometric range. At the same time, we can also get the pseudo range. So what we do, we calculate the difference between those two, then we could get or measure the errors and apply the corrections. Now, what we could do with those corrections to send them to the next user so they can benefit from them. How do we send these? Either via VHF radio or through a communication satellite. Now, this user, if they go a bit further, we will see what's going to happen. The problem is that these errors are spatially correlated. And obviously what we send here is a bundled error correction sent to the user around us. So just to give you a little bit of idea what happens to the correction, how it degrades with space or when the user is further from the reference station. If you look at this orbit correction, if we try to project it on the line of sight of the user, we see that if we go a bit further, it's going to degrade even more. Sorry. So that tells us that the further we go, the less relevant this bundled correction is going to become to the user. So the answer to this is what we call a wide area differential, like EGNOS or WAS. So how does it work? Very similar concept, but this time we have a wide area reference stations. That's a network of reference stations with known coordinates as well. So we try to break into these corrections. We model them separately. Where they were bundled corrections depend on the distance. Now we try to unbundle them. So we study their individual spatial correlation. So we do what we call a system dimensioning according to spatial correlation. And then everything again is sent to the master control station, like orbit corrections, IONO, and clock, and then sent to the users via a communication satellite. We have a number of those systems around the world. We have in America, WAS. We have CDCM in Russia, EGNOS in Europe, BDS-BUS in China, and then in Japan, the MSAS. So we could confidently say that we're reaching a global augmentation system. The second type of measurement is the carrier phase. And this one has various frequencies, as we can see. It has the L1, L2, and L5. So what's the difference between the code phase and the carrier phase? As its name means, it's a carrier. It means we modulate the code on it, so it carries the code. And the reason why it can do that, because it has a much higher frequency. So how do we measure the carrier phase? Again, we have a receiver and we have the satellite. Now this time, the carrier is coming down with a number of cycles. Now the receiver tries again to create a replica to measure these cycles. However, it can only measure the little part down there that we call phi 0, which you can see here. So now we know phi 0, which is measured by the receiver. We know the errors, we could model them. We know lambda from the previous slide. What we're trying to guess is NO. Once we do that, we can then calculate the whole distance between them. Now, this carrier phase measurement is much more accurate than the code phase, and we can see that it gives us millimeter or centimeter accuracy. So is GPS or GNSS vulnerable? The answer, yes, we all know that there's a lot of interference. One of them is jamming, and this is the complete deafening of the signal. We have spoofing and mickening, where we can fool the signal by sending it either a new signal that looks similar to my original signal, so we can follow it or trace it, or we can tamper with the existing signal by changing it, and again, we can fool the receiver, and the receiver can follow these positions. Then we have signal degradation, which could happen from so many things like solar storms. We have space debris and junks, and we have anti-satellite systems that could also affect GNSS. So now that we talked about all the legacy GNSS, we want to introduce the low Earth orbit GNSS. So the difference is that LEO is at a low altitude between 160 and 2,000 kilometers. and they have thousands of satellites versus the MEO ones that we just talked about. They are at an altitude between 2,000 and 36,000, and they have dozens of satellites. Now, the latency for LEO is quite low, which is good. For MEO, as we know, it's medium. Traditionally, LEO was for comms and Earth observations, but now we're trying to introduce also PNT on LEO. When it comes to MEO, MEO, as we know, is for navigation, for GNSS, and it has a global coverage of PNT. So this slide is from ESA, and that's their future project for LEO PNT. So the promise is for them to have purpose-built LEO PNT signals, different from the legacy signals. They're also promising that we will be able to fuse the PNT with SATCOM on the same payload. We will also be able to use signals of opportunity from third party, of course, if we can overcome problems like interoperability and compatibility. The second promise, which is very important as well, is the diversity of the frequency. As we know that MEO usually is on the L band, the legacy GNSS. This one is promising also to have the KU and the S band. The second thing that they are also promising to do with LEO is to put the 5G non-terrestrial communication for a telephony. So the mobile service on LEO. So is LEO perfect? No, LEO systems face timing precision challenges due to the rapid movement and the higher Doppler shift. Of course, we can have atomic clocks like we have on the legacy GNSS. However, like we said, these clocks are quite expensive, and deploying them on thousands of satellites is a challenge. MEO doesn't have that problem. As we know, they have better timing precision due to the atomic clocks. Now, when it comes to multipath, given that LEO is much closer to Earth, their signals are less likely to suffer from multipaths, while MEO satellites are further away. Their signals travel longer distances and are more prone to multipath interference. So now that we talked about Earth observation and GNSS, let's see if there are any synergies or benefits of GNSS to Earth observation. And the good news is that, yes, there are a few technologies. One is reflectometry. The second is refractometry or radio occultation. So what is reflectometry, or we call it GNSS-R? GNSS-R uses reflected GNSS signals to analyze the Earth's surface and geophysical parameters. So how does it work? The GNSS receiver, which is the GNSS-R, works as a bistatic radar system, where it receives or captures both the direct signal that is coming from the original GNSS and the reflected signal. Now, we have two measurements that come out of it. One is called the signal delay, and the second is the Doppler shift. The signal delay is the time taken for signals to travel from the satellite, reflect off a certain surface, and return to the receiver, while the Doppler shift, as we know, is the frequency changes due to the relative motion between two things. Here could be the satellite and the receiver. Now, those two measurements combined, we can generate something called the delay Doppler map, which provides insights into surface properties, of course, using all the methods that Professor Roman has just mentioned in classification. If we want to dig a little bit deeper into those, so what is time delay? Time delay is the extra time it takes for that reflected signal to reach the receiver compared to the direct one. Obviously, the longer the path, because it has bounced off the surface, the more delays the signal is. And what does it tell us? It shows us things like the geometry of the reflection point, the height and the structure of the surface. So to give you an example, if it's a flat ground, we can have a short time delay, but if it's mountainous or we have a rough area or rough sea, it's a longer path. When it comes to the Doppler shift, it's a change, like we said, in the frequency caused by relative motion between the satellite, the surface, and the receiver. It is important because, as we know, moving objects or surfaces like waves cause frequency shifts. Now, what does it tell us? The motion and the orientation of the reflecting surfaces. And always we remember that there's a relationship between the Doppler shift and the nature of that object. So this table summarizes it. Time delay is the extra path length of that reflection. So it's related to geometry and elevation. The Doppler shift, because it's a frequency change due to movement, it tells us about motion and surface roughness. So each reflection point on the surface produces, like we said, a unique combination of DDM, which becomes like a fingerprint of the surface condition. So if it's a coherent reflection, this occurs over a smooth surface. So we know we have a calm water body, for example. If these reflections are incoherent, it happens over rough terrain or turbulent water. So an example of this is the CYGNSS, or the Cyclone Global Navigation Satellite System that was used in the US. This system consists of 8 small satellites in LEO orbits. Each one was carrying a GNSS-R. The satellites track the reflected GPS signal from the L-band of the ocean surface, like we can see in the picture, measuring the surface roughness caused by those winds. In 2018, Hurricane Michael took place, and it was a tough one, apparently. Usually, the heavy rains that occurred during this period were obscured by the microwave sensor didn't really see those, but Cygnus penetrated the storm, measuring the winds over 65 miles per hour and trying to detect the tightening eye wall. The second technology is the refractometry. What does refractometry or radio occultation do? It measures the refractive index to determine how light bends when passing through different media. So GNSS signals, we know they are refracted as they pass through different atmospheric layers, like the ionosphere and the troposphere, affected by changes in air density, temperature, and humidity. Now, again, here we have different techniques. We cited 4 of them, like critical angle measurement, the total internal reflection, interferometer methods, and spectral refractometry. So what is important to notice here, the signal delay measurement, which is the time delay analysis that reveals the atmospheric conditions, the temperature, the pressure, the humidity. The excess phase processing, so this is the phase shift that helps derive refractivity and climate variables. The limb sound geometry, which measures the signal curvature for high resolution vertical profiling. Dual frequency measurements also is quite important because it analyzes multiple GNSS frequencies to correct that ionospheric delay and the precise orbit determination, because it ensures accurate satellite positioning for data interpretation. Now, what are the applications of GNSS radio occultation? It can be used for weather forecasting, could be used for climate monitoring, for ionospheric studies, atmospheric river observations, and many more. The advantage of it is that it has a very good coverage, it has very good high vertical resolution, and it's an all-weather capability. Like we said, sometimes the ground sensors can be obstructed, so this can take over. It's also good for long-term suitability, especially if we're doing scientific research. So this is an example of a radio occultation. So in China, they created the Feng-Yang meteorological LEO satellite, and they had various generations of it. The first generation, which is in the table FY3C, was a system that doesn't see Galileo, cannot read the signals from Galileo, while the new generation, the 3E, can actually see Galileo, or the reflected signals from Galileo. So that's a step up. As we can see, it can give us in positioning, it looks at 3 systems, in occultation, 24 satellites as well. So this one, the FY3E, which is the second generation, is a dual functionality. So it has both the GNSS RO and R. So it works on those 2 technologies. When we compared it to data from the Met Office and the ECMWF, we can look at the straight line here. It seems that it has very good accuracy and very good performance. So it's quite a reliable system. This is, again, the mission, the payload. The payload is called GNOS-2, which is put on those satellites. And it was very helpful in looking at things like the typhoon INFA in the Western Pacific Ocean. This typhoon took place in July 2021. Also, it was important in the Henan's 2021 extreme rainfall to look at soil moisture and moisture transport as well. Now I'm gonna go back to Alejandro to speak about how we can integrate those platforms together. Thank you.
Thank you very much, Mireille. Can we go to the next slide, please? Well, one good example of a EO PNT integration platforms is Australian bushfires in 2019 and 20. In this case, study EO and PNT integration supported emergency management during the 2019 and 20 Australian bushfires. For example, they used the Himawari 8 and Sentinel-2 satellites. Himawari 8 is a it's a geostationary satellite, and Sentinel-2 is from the Copernicus constellation. They provide near real-time imagery for active fires. GPS enable geofencing, alerted civilians, and helped emergency responders coordinate. And what is geofencing? Geofencing is to create virtual boundaries around the high-risk area, for example, triggering automated response when users enter or exit the zone. This integration of EO imagery, GNSS positioning, and GIS analytics is a powerful tool for real-time disaster management. Next, please. Next slide, please. And one of the key points that integrates those technologies of GNSS and EO is GIS. GIS is Geographic Information Systems, and these systems are the backbone of EO-PNT integration. GIS links geospatial data with analytical tools to create maps, simulations, and models. And GIS enables visualization of GNSS tracked objects, overlay of EO-derived layers, for example, fire extent, vegetation health, etc., and spatial queries for risk assessment. Real-time dashboard also is made by these systems of GIS for decision support. The synergy between GIS, GNSS, and EO accelerates the transition from raw data to actionable insights. Next, please. Next slide, please. And also we can mention in the GIS that we have data integration, for example, combining EO, GNSS, field, and weather data into a special database, spatial analysis, modeling relationships, fire spread, wind patterns, visualization, the dynamic maps and risks, heat maps, decision support, tools for prioritizing evacuation zones, or resource allocation. EO and GNSS data become significantly more useful when embedded within a GIS analytical environment. Next, please. For this part, I would like to ask again Mireille to explain the benefits of integrating LEO and PNT. We are reaching the end of this of our presentation. Mireille?
Yeah, thank you. So basically, this is just to show the future architecture. This is what we hope to look like. So we have the MEO geo satellites on top, then we have LEO and the airborne systems like UAV, then assisted by ground-based systems where we could find things like IMU or SOUP. Now, this architecture, the promise of it is resilience, so multi-layer system of systems, GNSS, aided by terrestrial technologies to provide robust and resilient PNT. Also, connectivity should become much better, and the promise of the bi-direction PNT, that from LEO to MEO and from MEO to LEO, is quite an important thing as well. In terms of mutual benefits, we talked about reflectory and occultation. These, like we said, will help improve atmospheric error correction for both GNSS and Earth observation. They're highly feasible due to their low altitude, which enables high resolution, rapid response observation of atmospheric and surface conditions. The frequent orbits of LEO satellites also allow them to capture the repeated measurements over a specific area. The second point is the improved GNSS architecture through integration with future LEO GNSS. We just went over it. However, we also need to think about enhanced RMP through this architecture. So we will have hopefully better accuracy, integrity, availability, and continuity and availability. Improving performance in challenging environments and the promise of new communication and internet, such as the non-terrestrial 5G. We also have other mutual enhancement of Earth observation and PNT systems. So PNT systems, as we know, traditionally they provide accurate positioning, navigation, and timing, but that is added to Earth observation technique. Earth observation data helps refine the measurement errors of GNSS, MEO, and LEO signals, while GNSS allow things like georeferencing of Earth observation data. Some mutual applications, for example, terrain and surface mapping. This involves the use of Earth observation satellites, airborne sensor, GNSS-based measurements to create high-resolution digital models. These maps are critical, as we know, for urban planning, disaster management, agriculture, and many other applications. The second is enhanced security and interference detection. LEO, as it provides a unique vantage point for observing terrestrial GNSS interference, we're hoping that it will help us solve some of those problems. By characterizing interference sources and analyzing signal strength, spectral properties, and structural content. Finally, environmental monitoring for signal availability. The environmental factors that we talked about, like the conditions, space, weather, etc., can significantly affect the integrity and accuracy of the GNSS and Earth observation signals. Finally, there's this table. I think, Alejandro, maybe you can go through this. You tell us a little bit more about the Sentinels and what they do.
Yes, another example of mutual enhancement between EO and PNT is, for example, the ionospheric corrections that is needed for Sentinel-1, 3, and 6. Sentinel-2 and 5 doesn't need, but also every GNSS signal needs ionospheric correction. Then we can use EO and GNSS technologies to mutual enhance both technologies. Back to you, Maya.
Okay, so finally, these are just some thoughts to finish with. As we saw that the integration of Earth observation and PNT represent a pivotal advancement in geospatial intelligence. If we could harness the power of LEO-based PNT constellations, we could highlight how synergistic approaches can enhance positioning, accuracy, situational awareness, environmental understanding, and disaster response capabilities, which is a huge demand now. Several technologies and policy challenges, of course, remain open, like data harmonization, interoperability, and regulatory constraints. So addressing these hurdles require a concerted effort, not just between scientists, but also policymakers, industry stakeholders, universities, and the rest of the communities to develop standardized, secure, and resilient multi-sensor platforms. So I think we came to the end of the webinar. Thank you so much for listening. Please, if you have any questions or you'd like to get in touch, these are our emails. Thank you.
Thank you very much.